Welcome back to the third section of Chapter 6. In this section, we're going to kind of step away from vectors, although they're still going to be here, and we're going to take a look at parametric equations and motion. We have actually seen this a couple times already this year, but now we're going to be able to look at it with a little bit of vectors and a little bit of trig involved as well. So, our learning targets: graph parametric equations, use an algebraic method to eliminate a parameter and identify a curve, find a parameterization for a curve, find values of a parameter that produce part of a given graph, and then solve applications involving parametric equations and motion. So the very first thing is, what is a parametric equation? Um, Again, we've seen this already a couple times. A parametric equation is where we have both x equals and y equals, and they're both related to some third value, which is generally t. So x could be 2t and y could be t squared. This is very useful in projectile motion. You see it a ton in physics. Projectile motion is what happens when, like, you kick a football. You fire a Nerf gun or any other gun. You throw a ball. However it happens, to jump on a trampoline. We're going to look at kicking a football. If you kick a football, it doesn't go just straight up and down. It moves like that. Parameterizing it, x is the horizontal movement of the ball, which tends to be linear. I'm just going to call it a times t. And then y is the verticalness of the ball. Like if we just threw the ball straight up in the air and it came back down, that would be actually what this y looks like. And this is going to be affected by gravity, which we'll talk about. Feet per second, so this would be negative 16 t squared, and then plus some number b times t. What's fun is that if we know the velocity that it goes from, and we know this angle, we could make that initial vector. The initial vector is going to be the velocity times cosine of theta, comma, the velocity times sine of theta, to get those x and y components of what's going on here. And that would actually be the a and the b from up here. So we can actually use these vectors to do this. We're not necessarily going to get into that too much today, but that's just one of these applications where the vectors and the parametric equations really come together to allow us to do a lot of different things. So then we also have these parametric curves. Well, what are parametric curves? Just the graphs of a parametric equation, honestly. So we have the ordered pair xy. X is f of t, y is g of t. The functions defined on the interval is a parametric curve. Now, it's using the word functions. That does not necessarily mean it's a function in our definition. It should be it's the relations defined on interval, or the graphs defined on interval, or something like that, because these do not necessarily pass the vertical line test. Like we could have circles, we could have all sorts of stuff. So don't read into this as it's like, oh, it has to be a function. In fact, that's one of the nice things about parametric equations is we can graph things that aren't in fact functions. And then the equations are the parametric equations. So it's just the graphs of the parametric equations. The variable t is a parameter, and I is the parameter interval. What t values are we looking at? And so that's what the parametric curve is. We're going to be graphing some of these. Now we could graph these by plugging in points. and then seeing what we're doing. But that's not the way I would graph these for the most part. I would graph them using either Desmos or your graphing calculator. I'm going to actually show you how to use your graphing calculator right here to graph these things. For Desmos, to graph a parametric equation, you actually plug it in as an ordered pair. You plug it in as the x, let's say f of t, and then comma, g of t, just as an ordered pair, and then it'll give you the window for your parameter. I'll show you the example with an actual thing. So if we have x equals t squared minus 2 and y equals 3t, in Desmos we would just make an ordered pair that says t squared minus 2, comma 3t, and then it would ask us, like, what does t equal? It starts out with negative infinity to positive infinity, but you can just narrow that by clicking and changing the value. So let's say we want it from -3 to 1. All right, well, let's see what it looks like in a graphing calculator. So I have my TI-84 plus here. That's what we have in the classrooms. It's kind of the standard. Any TI-84 or 83 is going to do the same. The older ones won't have quite as many of the options when we get into stuff. The resolution's a bit better here, but that's it. So you're going to have to excuse I have to film the calculator separately, and then I have to do an audio over it. It was jumping around a little bit, and so you'll see what I'm talking about, but I apologize for that in advance. So the very first thing we'd want to do is we want to go to the mode button, and we need to change the mode to parametric from function. And now if we go to y equals, notice it's not y equals anymore. It's x equals y equals. So we have x1, y1, x2, y2. I'm just clearing out what I already had in there. Here's where it's like trying to jump around and it's having trouble getting up to x1. I'll get there eventually. I tried to click, that didn't work. Nope. All right, we're on x1. Now we just type it in. X squared or t squared. And for t, we just go to that same variable button that usually gets us an x. Now it gets us a t because we're in this mode. Then we can go down to the second one. 3x. And now we can go to the window to set that interval, the t min and t max. That's what we're looking for the interval. So we're going to go from -3 to 1. And then graph. Oh, and find out that my window was set weird. So I'm going to zoom it back to a standard window, so 6. But now that changes the t, so I have to change the t interval again. Once you get that set, you shouldn't have to change it. All right, and we have our graph. Notice this is not a function because it fails the vertical line test right here. So it's not a function, but we can still graph it. And so we get that graph. We could graph it using other windows, like what if we have -2 is less than t is less than 3? For this, I just went to the window, changed my t interval. Instead of -3 to 1, we're going from -2 to 3, and we get this graph. What about from -3 to 3? Well, if this is -3 to 1, -3, and then it goes this way to 1, this one's -2, goes this way to 3, this one should be the full thing. In fact, it is. So that's graphing parametric curves. Again, you can use your calculator, you can use Desmos. Either way, I wouldn't really do them by hand because they can get kind of crazy. And I mean, if we were spending like a full chapter or so on parametric equations, maybe we'd get into that, but we're not spending that much time. So we'll be eliminating a parameter. eliminating a parameter is changing it from parametric back to a regular just xy equation because we're getting rid of that parameter t. So how would we do it? We know we want our equation to be y equals something, generally speaking. Well, we already have y equals something. We have y equals 2 minus t. Well, we don't want it to have t, we want it to have x. Well, here I have x relating to t, so we would want to solve that equation for t. So we can start by subtracting 1, and we can divide by -2 to get t equals -1/2 x plus 1/2. Then we're just going to plug that into this t. So we have y equals 2 minus t, which was -1/2 x plus 1/2. We can distribute and combine our like terms to get y equals 1/2 x, and then 2 minus 1/2 is plus 1.5. So this turns out just to be a line with a y-intercept of 1.5 and a slope of 1/2, which, as we are going to look at some of these things in a minute, we'll actually see that, oh yeah, that actually is a line. So what if we had something like the equation we just had? And the interval would be just infinite, like at -infinity to +infinity. What if we had one that was like what we had? We would do the same thing, solve for t. So x plus 2 equals t squared. So t is going to be the square root of x plus 2. But remember, when we square root both sides, we get a plus or minus, because either positive or negative t could be in there. Plug that in over here for y. So y equals plus or minus 3 times the square root of x plus 2. We could square both sides if we really wanted to. This is two functions because we had the square root function, but we also had that negative square root function. That's why that's there. If we squared both sides, we could get y squared equals 9 times x plus 2, which we'll see in a future chapter when we are looking at conic sections, that that's a sideways parabola. Because it is a parabola, it's just tipped on its side. But we'll get to that later. But that eliminates the plus or minus. What if we had something like this? X equals 2 cosine t, y equals 2 sine t. Here we wouldn't really want to solve for a t, because we'd have like an inverse cosine, which we'd then have to put into the sine, and that's going to become a bit problematic. Well, what else could we do? We have cosine and we have sine. If we think back to our identities, there's one identity that I said was really important, that was beyond just the basic what they are, and that would be the Pythagorean identity. If they were both squared, then we could actually do stuff with them. So let's square everything here. X squared equals 4 cosine squared t, and y squared equals 4 sine squared t. We can add them together. X squared plus y squared is going to be 4 cosine squared t plus 4 sine squared t. Factor out of 4. X squared plus y squared equals 4 cosine squared t plus sine squared t, which is that Pythagorean identity, which equals 1. So x squared plus y squared equals 4. That's the equation of a circle centered at the origin with a radius of 2. If we graphed these original parametric equations, we would actually have a circle centered at the origin with a radius of 2. So it comes out to be the same. This is the other way that you could do it. So we can eliminate a parameter by solving for t in the x equation and then plugging that in to the y equation. Or square both of them, specifically when we're dealing with trig, and then add them together so that we can use that Pythagorean identity. Those are the two ways that we'll be doing. I mean, there are a lot more complicated ways and stuff, but we aren't getting to those in this one topic that we are looking at this. Lines and line segments. How do we make equations of lines parametrically? Well, if we have a line that goes through the points -2, 3 and 3, 6, the first thing we'd want to do is let's find the vector. Let's find the vector AB. So to get from -2 to 3, we're adding 5. And to get from 3 to 6, we're adding 3. So the vector AB is 5, 3. That gives us the direction. And then we can multiply by something to give us whatever magnitude we want. And so if we have a starting point, which could be either of the 2 points, it could be any point along that line. You could find the midpoint. I would just start it at A. But if we have the point A and we add the vector, we would get to B. We could add any number times the vector. I'm going to use T is that. And that's going to give us this line. It's called the line. L is going to be the starting point plus T times the vector to go to another point. So we can split this out into the x and y coordinates. So this line is going to be x equals the x starting point, -2, and then plus, like basically the x slope is 5, so 5t. And y will be the y starting point, 3, plus the y slope, which was 3t. And so we just could then plug in values for t. When t equals 1, we get -2 plus 5 was 3, and 3 plus 3 is 6. When t equals 2, we get -2 plus 10 is 8, and 3 plus 6 is 9. So we'd have the point 8, 9. T could be 1/2, t could be negative, t could be any number. It does not have to be a whole number or an integer. It can be any number, but we would get all the points that are on the line connecting A and B. What if we want a line segment? With a line segment, we just have to limit our interval. So instead of it being t being anything from -infinity to +infinity, we're going to shorten it. And we just need it so that when it's at one end of the interval, it equals 1 point, and when it's at the other end of the interval, it equals the other point. So we could plug the points in for x and y and solve for t to see what it's going to be. But what's fun is that if we know the two endpoints, like in this case a and b, and we use these two endpoints to find that vector for the slopes, the interval is going to be from 0 to 1. Because when t equals 0, we start at A. When t equals 1, we're at B. In this case, like 5, 3 doesn't really reduce much. But if it was, say, 6, 3, that would be the same as 2, 1, right? I mean, we could factor out that constant multiplier. But if you don't simplify it or anything like that, and you start at one endpoint, you go to the other, it's always 0 to 1. And then t could just be anything in between that. So that really simplifies that process a lot. And that's for a line segment. For a line, you do not need to shorten that interval at all. So that's a quick review and a little bit more on these parametric equations, parametric curves. I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.